In this last presentation on magnetism, we will talk about transformers, which is one application of electromagnetic induction. So a transformer is an electrical component that basically allows the voltage in a system to be increased or decreased. And transformers will only work with alternating current, so we can't use a DC battery to do this. And of course, it's based on this concept of electromagnetic induction. And there's a lot of different everyday devices that use transformers. One thing that you're probably familiar with but maybe did not realize that it was a transformer is your laptop cord. So you plug your laptop in to the outlet, you have a plug for your actual laptop, and then there's usually some type of a box that is between those cords, and inside that is a transformer. Neon signs that you see also use a transformer. It's a different type of transformer. We're going to talk about the different types, but here, in order to get the gas inside of those tubes to glow, you have to have a very high voltage, so plugging it into the outlet without the transformer would not cause that, that gas to actually glow. Also power transmission, so we see transformers in power stations as we look at the different power distribution as it gets to our homes, and then also in the lines, and we'll see a picture of that on the power lines right before it gets to your house. So the basic concept of a transformer, and this is just one example of a transformer, is that you have an input coil, it's called the primary coil, and that's connected to AC. So here is, in my picture, is this transformer, and on the left-hand side over here are these coils, and that's called the primary circuit. And it is connected, let's say, to an outlet, so it's connected to an AC voltage supply that's alternating in time. These coils here, because they're in a shape of a solenoid, will actually produce a magnetic field. And that magnetic field will go through the center of the coils. That's what these dotted lines represent here. That's the magnetic field. Now, because the current through these coils is changing in time, that means the magnetic field that passes through that coil is also changing in time, and it's oscillating. So it's going in one direction for the magnetic field when the current goes in one direction, and it might be getting bigger and bigger as the current gets bigger and bigger. And then as it gets, as the current decreases, the magnetic field gets smaller and smaller, and then it switches direction and it goes the other direction. This particular coil is wound around a material that is a magnetic material. So in this particular case, this might be a big piece of iron, and it's a continuous piece of iron. And so we know that iron is a magnetic material and that it reacts essentially to magnetic fields. So when the primary coil produces a magnetic field, that magnetic field goes through that iron core, but it also wraps around to the other side, and on the other side of the transformer we have what are called the secondary coils, or the output coils. And so there's again these coils that are wrapped around. They are not connected to a power supply, they're just connected to a light bulb. But the idea is that this magnetic field that passes through the secondary coil that came from the primary coil is changing in time. So it's getting bigger in one direction and then smaller, and then it changes direction, and it's oscillating back and forth, like taking a magnet and moving a magnet back and forth in that coil. And of course, a changing magnetic field through that secondary coil causes a voltage to be induced, and that voltage can light the light bulb. So this is how a basic transformer works. You have to have alternating voltage in the primary coil in order to get a changing magnetic field through the secondary coil. Both of the coils are wound around the same common magnetic core like iron. So it turns out there are two different types of transformers. There's a step-up transformer, and a step-up transformer, it produces a greater voltage in the secondary coil as compared to the primary coil. So this is a picture on the right of a step-up transformer over here. In a step-up transformer, the input voltage over here, the primary voltage, will be less, and the secondary voltage coming out will be greater than the voltage that was put in. And one of the things that you should notice about this picture is that the number of turns in the secondary coil for a step-up transformer is greater than the number of turns of wire in the primary coil. So secondary coil has more turns than the primary for a step-up transformer. We're going to talk about this a little bit later, but although the voltage is stepped up in the secondary coil, the current in the secondary coil is actually less. So the current over here will be less than the input. A step-down transformer is just the reverse. With a step-down transformer, you have some input voltage over here in the primary coil, and the output voltage in the secondary coils will be less. So it produces a smaller voltage in the secondary coil, and it's exactly opposite in terms of the number of turns. So if you have a step-down transformer, the number of turns in the primary coil will be much greater than the number of turns of wire in the secondary coil. Exactly opposite to a step-up transformer, the current in the secondary coil is actually greater. So the step up and the step down refers to what happens to the voltage in the primary or in the secondary. If it steps up, the voltage will be greater in the secondary. If it steps down, the voltage will be less. So it turns out that there's a relationship between the number of turns of the coils in the primary and the secondary and what the voltage is that you get. So if you take the ratio of the primary voltage input divided by the number of turns that you have in that primary coil, it has to equal the voltage that you get out over the number of turns in the secondary. The way that we write this is that the voltage of the primary over the number of turns in the primary is equal to the voltage in the secondary over the number of turns in the secondary. So we have this ratio relationship. Voltage to turns is basically constant in a transformer. If we wanted to, we could solve for the voltage here of the secondary by multiplying both sides of this equation by the number of turns in the secondary, and we get that the voltage in the secondary is the ratio of the number of turns in the secondary to the number of turns in the primary multiplied by the voltage of the primary. So we can see that if the number of turns in the secondary is less than the number of turns in the primary, this fraction will be less than 1 and that voltage will be less, versus if the number of turns in the secondary is greater than the number of turns in the primary, this fraction will be greater than 1 and the voltage of the secondary will be greater. The other thing that we know about transformers and we know about physics in general is that energy cannot be created or destroyed. So it turns out that the rate at which energy is produced in the primary coil, in the input, is exactly equal to the rate of the energy that's transferred to the secondary coil, or the output. This is in a perfect world. So remember, perfect worlds, there's no friction, there's no air resistance, there's no loss to heat or light or anything like that. So in a perfect transformer, the power that you put in from the primary source is equal to the power that you get out. And we know that power in general is current times voltage. So if you take the current times the voltage in the primary coil, it has to equal the current times the voltage in the secondary coil. And of course we write this as current times voltage. Current is I, voltage is V. And that, so current times voltage in primary has to equal current times voltage in secondary. So let's look at an example. We have a transformer and it's plugged into a wall outlet which has a primary voltage of 120. Now remember, the voltage is not constant, it's actually oscillating in time, but this voltage represents what would the equivalent DC voltage be. So that's our primary voltage. The number of turns on the primary coil is 2,400 turns. It says if the input current to the primary coil is 0.2 amps, what is the power in the primary coil? So we know the voltage in the primary coil, it's plugged into 120 and it's drawing 0.2 amps of current. So we know that the power is the current multiplied by the voltage. The current is 0.2, the voltage is 120, so that's 24 watts. So the power of the primary coil is 24 watts. We also want to determine the voltage across and the current through the secondary coil of a transformer that has the following number of turns. Suppose we have a transformer that has 600 turns and a transformer that has 4,800 turns. One of the things that we actually already know if we determine the power in the input coil, then we automatically know the power in the secondary coils. So we can fill in this table and we could say that the power in transformer 1 or transformer 2 or whichever transformer we have has to be 24 watts because energy is essentially conserved. So the power in is equal to the power out. All right, so let's start with the first transformer and let's determine the voltage across that output secondary coil and the current in the secondary coil. So this is what we know. So we know the primary voltage is 120, we know the primary current is 0.2, and we know the number of turns in the primary is 2,400. We want to find the voltage in the secondary and the current, and we know the number of turns in this transformer is 600. So we can go to our relationship for a transformer that says that the voltage in the secondary is the ratio of the number of turns in the secondary to the primary times the voltage of the primary. The number of turns in the secondary is 600, number of turns in the primary is 2,400, and the voltage is 120. If I look at this fraction of 600 over 2,400, that's actually 1 over 4. So 1 over 4 multiplied by 120 is 30 volts. So we know the voltage in transformer 1 is 30 volts, and we can figure out, is it a step up or a step down? Because the voltage was 120 and now it's 30, it's a step down transformer. We also want to know what the current is. And so we know that the power in the secondary is 24 watts. And power in the secondary is the current times the voltage. So we know that that power is 24, and that has to equal the current times the voltage, where my voltage in my secondary is 30 volts. So if I want to solve for the current in the secondary, I would divide both sides by 30, and I get 0.8 amps. So the current has actually gone up. So let's think a little bit about this. So the ratio of the number of turns was 600 to 2,400. It was a quarter. And as a result, the voltage decreased by a factor of 4. Right? It's now 30. But what happened to the current? The current was 0.2, and now it's 0.8. So the current actually went up by a factor of 4. And so in a transformer, you can't get something for nothing. So we've dropped the voltage and we've increased the current in order to keep the power the same in that particular coil. So however much the voltage drops, the current will increase by that same amount. All right, so we can go through the same process for transformer 2, and we want to solve for the voltage of the secondary, current of the secondary, and so on. So we know that the voltage for the secondary is the ratio of the number of turns of the secondary to the primary times the voltage of the primary. In our case, transformer 2 has 4,800 turns. The primary had 2,400, and I can multiply that by the voltage of the primary. When I take this ratio of the number of turns, I realize that that's 2. So that means that the voltage increases to double what it was in the primary. So 240 volts. So we now know that this is a step-up transformer because the voltage was 120 and now it's 240, so the voltage stepped up, increased by a factor of 2. We can also look at what happens to the current, and again we know that the power stays constant, so the power in the secondary is equal to the current times the voltage. The power is 24 watts, the voltage is 240. I can divide both sides by 240, and I get that the current is 0.1 amps. So I noticed that the current was 0.2 amps, and now the current is half what it was before. So in this particular transformer, the voltage was doubled, and the current reduced by a half. So transformers are actually very important because we want to be able to step up or step down the voltage based on how that power is transmitted through the lines. So it's much better to have high voltage through the lines versus high current. And we're not going to go into all the details of that, but basically when you have high current, you can have more losses in the lines. But what happens is the voltage is stepped up before leaving the power station. So you have a transformer that steps up the voltage and steps down the current. That's this picture right here with the transformer. And then it's transmitted through the lines, and then before it gets to the final stages, the voltage is stepped down for distribution near cities. So here's a distribution center right here. And then it's stepped down still yet again before it gets to your house to make sure that you have that 120 volts going into your house. So this is what a transformer would look like near your home on one of the power lines. And then this is sort of one of those, you'll see these power stations along the way. So transmitting power for large distances is really important that we use AC, because we can use these transformers, we can use this concept of electromagnetic induction. We consider one more example of a transformer. In this particular case, we have different information that's given. So a transformer has 50 turns in its primary, and 12 volts is connected to the primary. Again, this is AC, so it's the equivalent of 12 volts DC, but that is alternating voltage. We want to know what is the number of turns that has to be set up in the secondary if the voltage in the secondary is going to be 60 volts. So this is a slightly different problem in terms of what's given, but we would set it up the same way. So we know the number of turns in the primary is 50, and we know that the voltage is 12 volts, and we want to have 60 volts in the secondary, and we want to know how many turns we have to put there. So the first thing we realize is that this is a step-up transformer because the voltage in the secondary is greater than the voltage in the primary. And so that means the number of turns in the secondary is going to have to be greater than the number of turns in the primary. And actually, we could sort of think through this, how 60 is related to 12. So if 60 is 5 times 12 is essentially going to give us 60. So that sort of tells us as an indicator of what the number of turns is going to have to be here. It's going to have to be 5 times the number of turns in the primary. But let's work this out. So we know that for a transformer, the voltage of the primary over the number of turns in the primary has to equal the voltage in the secondary over the number of turns in the secondary. Now our goal is actually to determine the number of turns in the secondary. So what I can do is I can multiply both sides of this equation by the number of turns in the secondary, and then I can divide out. Now one way that I learned to do this at a very early age is just to do this cross multiply with fractions. So I can bring the two terms that are in the denominator up to the numerator on the other side. So the number of turns of the secondary would go on the left, the number of turns on the primary would go on the right. But in this particular case, let's go ahead and put the numbers in first, I guess, the way I have this set up. So the voltage of the primary is 12. The number of turns is 50, the voltage in the secondary is 60, the number of turns in the secondary is what we're looking for, and now we can do this cross multiplying, right? So I can bring the number of turns to the secondary to the numerator on the left, and the number of turns from the primary over to the numerator on the right, right? So basically doing this cross multiplying with our fraction. So I have 12 times the number of turns of the secondary equals 60 times 50. To solve for the number of turns in the secondary, I can multiply 60 times 50 and I get 3,000. And then I can divide both sides by 12. And when I divide both sides by 12, I get 250 turns. So I sort of talked through this ahead of time, and I got the correct answer. So the voltage in the secondary is basically increased to 5 times what it was in the primary. So that means the number of turns has to be increased by 5 times the primary turns, and 5 times 50 is 250. So we could sort of think through this a little bit conceptually. Of course, this is a step-up transformer because the voltage steps up. The second part of this question says, if the current in the primary was 4 amps, what must be the current in the secondary? So I know the voltage increased by a factor of 5, and so that means the current is going to have to decrease by a factor of 5. But let's work this out. So we know that in a transformer, the power input is equal to the power output. And power is current times voltage, or voltage times current. So the voltage of the primary times the current in the primary has to equal the voltage in the secondary times the current in the secondary. So the voltage of the primary is 12. The current in the primary is given to us as 4. The voltage in the secondary is 60, and I want to know how much current that has to be. So 12 times 4 is 48. That has to be equal to 60 times I. If I divide both sides of this expression by 60, I get 0.8. So the current has decreased by a factor of 5. So if you took 4 and you divide by 5, you would get 0.8. So again, sort of this ratio of this relationship between number of turns and voltage, and how the voltage increases, then the current has to decrease by that same amount, and vice versa.